Now, phagocytosis. This is the last step of acute inflammation and it involves removal of the pathogen by a leukocyte. Now again, folks, we're going over the same process. The pathogen overcame the physical and chemical barriers to infection. The PAMP, or the bacterial cell wall component, binded to pattern recognition receptors on epithelial cells or cells directly. This led to the activation of complement, and complement resulted in opsonization of pathogen, vasodilation, the release of chemoattractants, and increased permeability. This then enabled the neutrophil to reach the right site of infection and make its way towards the pathogen. So that would be an introduction, for example, for a phagocytosis assay, to be able to give me an idea of how we got to the point where the neutrophil is going to phagocytose the pathogen. Okay, and here we are. The neutrophil has undergone rolling margination, diabetesis, and then it reaches the opsonized bacteria. So, once it reaches the opsonized bacteria, it combined with the bacteria through its CR1 receptor by binding to C3b or C4b. And once it's bound, it takes it into the cell and forms an early phagosome. And when it forms an early phagosome, the phagosome has got a relatively high pH. The phagosome then fuses with an early endosome, which has some proton pumps. So it now gives the phagosome some proton pumps, which enables the phagosome to become acidified. And this is an important feature because in order for the enzymes to become active in the phagosome and in the phagolysosome, it must reach a low pH. As you can see here, the late phagosome has a pH of 4.5. At that point, a molecule called EEA1 enables the phagosome to make its way towards the lysosome. And once it reaches the lysosome, the two fuse together to form a phagolysosome. Now, the lysosome contains a range of lytic enzymes and proteases that will help degrade the pathogen. So the phagolysosome then subsequently causes the degradation of the pathogen within the lysosome. But how does it do that? Okay, so how does the neutrophil recognize the pathogen? The microbe will be opsonized either with complement or antibody, C3b or C3b or C4b or antibody. The neutrophil then binds to the opsonized bacteria, and it does this through binding to the antibody through the Fc receptor. The Fc receptor binds to the Fc region of the antibody, which enables it to engulf the pathogen and the antibody. Or alternatively, the Fc receptor present on the neutrophil will bind to C3b or C4b, which again will enable it to uptake the pathogen into the cell. And here we go. You get extension of the pseudopods, little cell membrane extensions, which encapsulate the bacteria and enable it to be brought into the cell. At that point, you get an early phagosome. The phagosome then fuses with an endosome loaded with proton pumps. And the proton pump enables acidification of the phagosome. And in the late phagosome, the pH is around 4.5. At that point, the phagosome, which contains EA1, is led towards the lysosome, which subsequently fuses. Once a phagosome fuses with a lysosome, it becomes a phagolysosome. So that's a summary of the initial process within the cell of phagocytosis. So what happens in the phagolysosome? You need to talk about the respiratory burst which is oxygen-mediated degradation. And essentially, the process we're about to talk to involves a reduction of reactive oxygen species, which can then react with the molecular components of the microbe and subsequently degrade their protein, DNA, and other components to the point that the microbe is no longer functional and no longer viable. So the first enzyme used is NADPH oxidase. So NADPH and 2 molecular oxygen result in NADP plus 2 superoxide ions and a proton. Superoxide dismutase can then take two superoxide ions and hydrogen to make hydrogen peroxide. And the hydrogen peroxide can then react with chloride to form hypochlorous acid and hydroxide ion. HOCl then degrades into a proton and OCl minus, and it's the OCl minus that is the extremely potent free radical that's going to degrade the microbe. The hydrogen peroxide can also react with nitric oxide to form ONOO minus, which again is an extremely potent free radical which can result in degradation of the microbe. So in your essay you need to talk about respiratory burst and take me through the enzymes and the free radicals that contribute to degradation of the bacterial component. The other mechanism of degradation is oxygen independent. And folks, one of the major issues that I have when marking this essay is people forget to mention this part of the degradation of the component, of the pathogen. So oxygen independent involves lactoferrins, which sequester iron, and when you sequester iron, it makes it difficult for the bacteria to survive. Alternatively, you also have lysozyme, which interferes with peptidoglycan, which is a cell wall component. You also have the production of defensins, which form pores in the bacterial membrane, essentially causing them to degrade. And of course, you have other enzymes such as glycosylases, phospholipases, and nucleases, which will degrade the cell wall component, cell membrane, and nuclear material. Okay, so that's the phagocytosis. You need to talk about the actual process of getting the cell into the phagolysosome, and then take us through respiratory burst, and then take us through the oxygen-independent mediated degradation. And again, folks, at the end of the essay, you should be trying to give some sort of context to your essay. And what you'll talk about is what happens when you get defects in phagocytes or phagocytosis. So phagocyte cells such as neutrophils, monocytes, and macrophages are important against pathogenic bacteria and other intracellular organisms as well. And 2 genetic defects of phagocytes can result in severe infections which can result in fatalities. So the first is chronic granulomatosis disease. And this happens when you have defective NADPH oxidase, which basically results in the individual having defective oxygen-dependent killing. Again, you need to explain how this enzyme will result in defective immune protection. The other aspect is you can have type 1 leukocyte adhesion deficiency, LAD1. And in this case, the phagocytes lack C complement receptor 3 in their cell surface and therefore find it difficult to bind to C3bi on opsonized pathogens, and therefore the pathogen won't be recognized and taken up into the cell. There are 2 examples. Using your reading outside the topic, you should try and find other examples where you have genetic defects in phagocytes.